Assalamu alaikum, dear students. I welcome you to 38th lecture of probability and stochastic processes. In recent lectures, we are analyzing Markov chains, a special collection of random variables. And in the analysis of Markov chains, we were looking at the behavior of different states based on the values in transition probability matrices. We looked at one-step transition probability matrix and related it to one-step reachability. If entry in a certain ith row and jth column of one-step transition probability matrix is non-zero, it implies that at any sampling interval, if the value attained is the roth number, the state in which the random variable is assuming its value is the roth of that particular entry, then on the next step, the probability of moving from that state to the state marked by jth column is non-zero. That is, if at sampling instance n we are in state I, which is the row of that entry, then at sampling instance n plus 1, the probability of us observing a value which is equal to j, the column of that non-zero entry is that probability which is non-zero. So it's possible that we will move from state I to state j. It's possible that we will not. But probability of moving is non-zero. We may or may not, but depending upon how the sequence of random variable behaves, the probability of that thing happening is non-zero, and that probability is given by the entry in one-step transition probability matrix at ith column and at ith row and jth column. We use this one-step transition probability matrices to find the probability distributions. We saw that if we know the probability distribution of a random variable capital Xn, then to find the probability distribution at n plus 1 sampling interval or probability distribution of capital X n plus 1, you have to take the row vector of probability distribution at nth sampling instance and multiply it with one-step transition probability matrix. We extended this idea to n-step transition probability matrix and saw that if entry in ith row and jth column of an n-step transition probability matrix is non-zero, it means that from ith state with label I, we can move to jth state in n steps. And it is possible that if we are finding these n-step transition probability matrix, to find a matrix which has all entries non-zero. That has a special significance, as we'll see in today's lecture. So let's have a look at the values in an n-step transition probability matrix and what they imply. An n-step transition probability matrix looks like a matrix of values which are between 0 and 1 because they represent transition probabilities. So if we are looking at an entry Pn12, that represents probability of sequence of random variable assuming value 1 in sampling instance say m and assuming value 2 in sampling instance m plus n. In n steps, we can move from state 1 to state 2, and this entry represents that probability. We also saw that n-step transition probability matrix capital P with index n is also equal to capital P raised to power n, that is n-step transition probability matrix is nth power of one-step transition probability matrix. We covered all these ideas in previous lecture. Let's now look at a few interesting properties of an n-step transition probability matrix. Such a matrix is also called a stochastic matrix. And the properties that we are going to look at is that if you sum all these entries in any row of a stochastic matrix, whether it is one-step transition probability matrix or n-step transition probability matrix, sum of all entries in a row is going to be 1. Why? These entries represent probabilities of moving from state 0 to different other states. This row represents all possible jumps from state 0. So probability of moving from state 0 to any other state, which implies the whole sample space. So if you move from state 0 to all other possible states, which represents the whole sample space, probability of that jump, probability of that move is 1. We are saying that at sampling instance m, we are in state 0, and with probability 1, we are going to move some other state. And that state could be state 0 itself, which is shown here. So from state 0, we move to some other state with probability 1. Hence, if you apply the idea of partitioning of a sample space, you will know that sum of all these probabilities will be 1, that with probability 1 will move to either of the states in the whole state space. So sum of all these rows is going to be 0. We also talked about a special event where when you are finding n-step probability matrix, you find that all entries have become non-zero. Suppose for a certain value of n, this matrix has all entries which are non-zero. Then for all subsequent powers, the entries will be non-zero again. Why? Let's have a look at this argument in a graphic manner. Suppose you want to find the stochastic matrix for m plus 1 step transition probability matrix. On the right, this represents capital P m or capital P raised to power m. This is the m step stochastic matrix, m step transition probability matrix. And this is P1. If you want to find Pm plus 1, you take your Pm and multiply it with P1, one-step transition probability matrix. Now imagine all these entries are non-zero, and where I have empty spaces in P1, those spaces represent zeros. Hence, if you want to find the entry at ith row and jth column of Pm plus 1, you will take ith row of P1 and jth column of Pm and multiply them respectively element by element and then sum them. If you take such an inner product where we take element by element multiplication followed by summation, you will have a value which is going to be non-zero. Because all these values are non-zero, and sum of all these values from any row that we pick from P1 is also 1, hence the inner product is going to be a non-zero value. It's possible for P1 to have 0 entries, which mean that it's not possible to go from a certain state to another state in one jump, but it's possible that after you take a certain number of jumps, it's possible for you to go from any state to any state. So if Pm plus 1 or Pm has all entries non-zero, it implies that if you take a certain number of jumps, then you can move from any state to any state. So if we start with a one-step transition probability matrix which may have some 0 entries, implying that it's not possible to jump from a certain state to another state in one step, but if we continue finding higher powers of this one-step transition probability matrix, which represents n-step reachability. If an entry in n-step transition probability matrix is non-zero, it implies that we can reach from a certain state to another state in n gems, where starting state is represented by the row and the destination state by the column. So if we have a finite Markov chain with finite state space, only a small number of states, and after a certain number of jumps, it's possible to jump from any state to any state, and all subsequent jumps also allow you to reach from any state to any state, then this whole Markov chain is recurrent, because you can start from any state and after a certain number of jumps you can reach to any state, and from that state you can take that required number of jumps and come back to that state, and you continue reaching from one state to another and back. So this is a recurrent Markov chain which has a n-step transition probability matrix with all elements being non-zero. If we continue to take higher and higher powers of one-step transition probability matrix, then this n-step transition probability matrix has a tendency to converge to a unique matrix. We'll see in later part of this lecture under what conditions such a convergence is expected. But now let's have a look at a few examples of one-step transition probability matrix, its higher powers, that is n-step transition probability matrices, and see in certain cases such matrices will give you an intermediate matrix with all elements being non-zero, and in other cases it will not be possible to have such a matrix. The first example that you see on your screen is from that machine which gets broken and it is repaired in a local facility or a specialized central facility. We have seen its one-step transition probability matrix P, and you can see that some of these entries are zero, which imply that in one step it's not possible to reach from state 0 to state 1. State 0 means centralized repair facility, and if this gets repaired, it only goes back to state 2 or it remains in state 0. So in one step, certain states are not reachable. But if you take P2, the two-step transition probability matrix, you see that all these entries have become non-zero, which implies that if you are in any of these three states, it is possible with non-zero probability, no matter how small, for you to jump in two steps to any other state. And if you have this two-step transition probability matrix with all elements being non-zero and continue to take higher and higher powers of P, you eventually get a P infinity, a value of matrix to which all these sequence of matrices converge. And if you look at this P infinity matrix, it has constant rows. All rows are the same. And this is important for this matrix to converge to such a matrix where all rows are same and all rows give a sum of 1. That is the characteristic of a stochastic matrix. So this Markov chain with simple three-state state space and a given transition probability matrix converges to a transition probability matrix for large number of steps, which is given here with constant rows. By the way, these rows also represent the probability distribution in the long run. That is, in the long run, no matter how you start this Markov chain, probability of this machine being in state 0 is 4.3%, being in state 1 is 8.7%, and being in state 2 is 87%. Let's have a look at another example. This example is a random walk on 4 states with perfect reflection. If you are in state 1, with equal probability you either move to right or left in next step, and if you are in state 2 you move to left or right with equal probability. But if you are in state 3, at next sampling interval you must move back to 2. Similarly, if you are in state 0, you must move up to state 1 in next jump. Let's have a look at its one-step transition probability matrix, which is shown here. And if you take its second power, you will see that all entries do not become non-zero. There will be some entries which will be 0. If you continue to take higher and higher powers, you will see that if you take a power which is divisible by 2, that is an even power, you will get this matrix in the long run. And if you take an odd power, you will get this matrix represented by P2k plus 1. So if k is an integer, then P2k represents an even power and P2k plus 1 an odd power. So no matter how many times you multiply this speed with itself, you are not going to get a matrix which is constant, non-variant, and has all entries non-zero. By the way, in both of these cases, for even power and odd power, the sum of all the rows is still 1. They do represent stochastic matrices, but in this particular case, in the long run, n-step transition probability matrix is not going to converge to a unique value, but it will switch between these two matrices. Let's look at more complicated example which represents the transition of status of a person who is trying to perform Hajj, or if he has performed Hajj, he reapplies to perform another Hajj. The state space is shown here. This has 8 states starting from 0 to 7, and one-step transition probability matrix will be an 8 by 8 matrix. We can start with that, but let's have a look at the long-term evolution of this matrix when we take higher and higher powers of this matrix. If we take a power of this transition probability matrix which is divisible by 3, we'll get a matrix which will have some entries 0, some entries non-zero. Here I have shown long-term matrix P with an index 3k. If k is integer, then 3k is divisible by 3. So if you take a power of one-step transition probability matrix which is divisible by 3, this will be the kind of situation. Here red blocks represents values which are non-zero, and empty spaces represents values which are 0. So there will be a lot of zeros even in the long run. And if you take a power which is not divisible by 3 but gives a remainder of 1, you see this kind of distribution of non-zero values shown with green blocks. So if these green blocks represent values which are non-zero, then all the empty spaces represent values which are 0. And if you take a power which is not divisible by 3 and gives a remainder of 2, you get distribution of non-zero entries which are shown here graphically with blue blocks. So if blue blocks represents non-zero values, all the gaps represent 0 values. If you combine all these three, if you superimpose 3 matrices which we obtain by raising a power which is divisible by 3 or gives a remainder of 1 or gives a remainder of 2, you will see that it covers the whole 8 by 8 block. So some entries are divisible by 3, some entries are for the matrix which has a power of one-step transition probability matrix which is divisible by 3, they are represented by red, and green represents those entries which are non-zero for P 3k plus 1, and blue represents those entries which are non-zero if you take a power of 3k plus 2 for the one-step transition probability matrix. So for this case, the n-step transition probability matrix does not converge to a unique value but switches between 3 given long-term large number of step transition probability matrices, P3K, P3K plus 1 and P3K plus 2. So this Markov chain does not have a convergent, stationary, unique probability distribution. And we'll see why this is the case in next part of the lecture. The three examples that you just saw all represent recurrent chains. In first example, the stochastic matrix for large number of steps had all entries which were non-zero, and eventually it converged to a stationary matrix. In the case of second and third example, the stochastic matrices for large number of steps never had all entries non-zero. They always had some entries 0. The second example had a periodicity of 2. That is, in the long run, the stochastic matrices switched between given two matrices. And the third example had a periodicity of 3. That is, in the long run, if you continue to take higher and higher powers of one-step transition probability matrix, what you get is a periodic switching between 3 long-term matrices. So convergence of higher powers of one-step transition probability matrix to a unique matrix is an interesting subgroup of recurrent Markov chains, and such convergence represents a unique, stable, stationary, non-variant probability distribution. Now we will discuss the conditions under which the n-step transition probability matrix converges to a unique matrix. Such a convergence is desirable because then we can assign a unique probability distribution, which is the long-term probability distribution of different states, and this long-term probability distribution is invariant. It is not dependent on the initial probability distribution. So if a Markov chain has a non-variant long-term stationary probability distribution, then this probability distribution is applicable for all sampling instances which are large. If the Markov chain starts at sampling instance 0 and you move a certain large number of steps, by that time you have converged, and for that sampling instance the probability distribution will be the same as the probability distribution for the next step and the next step and the next step. So it doesn't matter from which initial probability distribution you start, you could have started with the same probability distribution, that is the non-variant one. If that's the case, then every next step you will have the same distribution. But if you start from a certain different initial probability distribution, you will eventually converge to a stable, stationary, non-variant probability distribution. And this is reflected by the fact that this n-step transition probability matrices converge to a destination value, which we can represent by P infinity. Infinity being the index, emphasizing that this is the value to which this sequence converges. Let's have a look at these relationships. You can see on your screen that if Pn, the n-step transition probability matrix, converges to a unique destination matrix P infinity, then mathematically we represent it as a limit n goes to infinity, Pn being P infinity, a unique destination matrix. Let's try to find the probability distribution at sampling instance n, where n is large. This is shown as limit n goes to infinity pi n. We are finding the probability distribution pi n for large values of n. And this is equal to this limit applied on pi 0, the initial probability distribution, and then multiplied by Pn. Since pi 0 is constant, not a function of n, you can take it out, apply limit to Pn, and you get pi 0 into P infinity, and this gives you a unique stationary distribution, which is pi. If you have reached this pi, then it does not matter if you move a few more steps, your probability distribution is going to be pi again. So if you have reached a point where probability distribution is pi, then it will be again pi on the next sampling interval and next sampling interval. So if you take this pi to be your probability distribution at any step, then the next step probability distribution is also pi. This is represented here, that if you have an initial probability distribution pi, you multiply it with pi, you will get next probability distribution, and that is again pi. If you look carefully at this expression, this is similar to the eigenvalue eigenvector concept. In eigenvalue eigenvectors, you had a matrix and you multiplied matrix, keeping matrix on the left side and the vector on the right side. But here the order is opposite. We have pi, which is a row vector, and you multiply this row vector with p, the matrix, and you get pi, the row vector again. So pi is a left side eigenvector of this one step transition probability matrix P. And if you multiply it again here with P, you are going to get pi again. So it does not matter if you multiply it with P or multiply this result with again P or multiply this with P square or P cube, you are going to get pi. So this pi is eigenvector of P or P square or P cube or P raised to power 4. And the eigen value is 1. If you look here, you pre-multiply pi with P and you get pi again. So recalling the ideas of eigenvectors and eigenvalues, this expression shows that if you have a one-step transition probability matrix and you consider this left-sided eigenvalues and eigenvectors, then pi is a special eigenvector with associated eigenvalue of 1. So this pi, which is stable, stationary, non-variant probability distribution, is an eigenvector of P, P square, or even P infinity, and associated eigenvalue is 1. So if you have this one-step transition probability matrix, you can perform eigenanalysis using MATLAB or any other software to find its eigenvalues and eigenvectors, and you can find pi, which is going to be the eigenvector corresponding to the eigenvalue of 1. Considering that this Markov chain and its associated one-step transition probability matrix represent a recurrent Markov chain, which gives you a n-step transition probability matrix with all elements being non-zero. Here is a word of caution though. If you are trying to do this eigenvalue eigenvector analysis using MATLAB and you issue MATLAB command EIG for eigenvalue analysis, it's going to perform the eigenanalysis for right-sided vector, column vector type eigenvectors. So it is going to assume that the matrix that you are going to give it is being analyzed for right-sided eigenvectors. But here we are working with left-sided row vectors being the eigenvectors and corresponding eigenvalues. So one way to do is you take your P, one-step transition probability matrix, and transpose it, and then perform the eigenanalysis using MATLAB and try to reinterpret the results. Wherever you are talking about columns, you should talk about rows, and wherever you are talking about rows, you should talk about columns. So be careful when you do eigenanalysis using MATLAB, because there is a row vector versus column vector problem that you must address. So if a Markov chain is recurrent and its n-step transition probability matrix converges to a destination value P with index infinity, then this destination matrix must have all rows which are also equal to the stationary probability distribution. Why is it so? Let's have a look at a slide. So if pi is an eigenvector and the Markov chain converges, then this relationship holds, that if you take pi, your stationary distribution, and multiply it with p or p square or even p infinity, you should again get pi. So if you open this pi in terms of its entries pi 0, the distribution, stationary distribution for state 0, the stationary probability value of state 1, and all the way to capital N, where capital N represents the number of states. Actually there are n plus 1 states because we start from 0 and have the last index being n. For this stationary distribution to be true for this expression, you should have this distribution, and this should be equal to multiplication of pi with this p. And the argument is that this p infinity must have all rows which are also pi. The reason is that this row vector, which represents stationary probability distribution, gives a sum which is equal to 1. If you take this row vector and multiply it with p infinity, then look at a certain value. Say you look at the first value of the resulting multiplication. So the first value must also be equal to pi 0, the stationary probability value of state 0. So how is it going to be possible? If you take this row vector and multiply it with the first column of p infinity, then you should get back your pi 0. This pi, the row vector, has sum which is equal to 1. So if you take a constant value here and multiply with all the values, take out the constant value, take this sum, this is 1, then that constant value is going to come up here. Hence, for all the values in the first column, you must have pi of 0. Similarly, for the second column, you must have a constant value pi of 1, and so on and so forth. So if this p infinity is the destination matrix for this convergent sequence of matrices, then this p infinity must have all rows same, and those rows must also represent this pi, the stationary distribution. We just saw that if we have a small finite state space Markov chain and it has a stationary long-term probability distribution, then its one-step transition probability matrix must have an eigenvalue of 1, that is a left-sided eigenvector eigenvalue. It must have an eigenvalue of 1 corresponding to a left side row vector, which is an eigenvector of this one-step transition probability matrix, and that row vector is the long-term stationary probability distribution of that Markov chain. That is condition on one eigenvalue and one eigenvector. That is, one eigenvector must be the stationary probability distribution and associated eigenvalue must be 1. Now the question is, what about other eigenvalues of this one-step transition probability matrix? If we have a Markov chain which has a total number of n, capital N states, then the one-step transition probability matrix is an n by n matrix. So are other higher n-step transition probability matrices. For all these matrices, we know that one eigenvector should be the stationary distribution with associated eigenvalue of 1. There must be some other condition on other eigenvalues and other eigenvectors so that this n-step transition probability matrix converges to p infinity. We are going to look at these other conditions which must be fulfilled by other eigenvalues and other eigenvectors of a stochastic matrix so that the Markov chain has a unique stationary probability distribution. First, let's look at a few examples of one-step transition probability matrices and their left-sided eigenvalues. The first example that you see on your screen is that simplified version of that machine which sometime breaks down with a probability of 0.1, and repair facility is so perfect that by next morning it always gets repaired, and with 90% probability it remains in working order by the next morning. So this was very simple Markov chain with only two states. Let's look at its one-step transition probability matrix P, which is being shown here, and here are its eigenvalues. They are 1 and minus 0.1. So existence of this eigenvalue of 1 shows that this Markov chain has a potential to give you a stable, unique probability distribution. We'll see what that distribution is. Actually, we have solved this problem in previous lectures and we have already found the probability distribution. Here, important thing to look is that indeed there is one eigenvalue which is 1, and hence this n-step transition probability matrix may converge to a unique destination value. The next example is the extended version of the same problem where we have three states 0, 1 and 2, and its associated one-step transition probability matrix have been shown to you many times, so I'm going to skip that and just going to show you the values of eigenvalues. The three eigenvalues associated with one-step transition probability matrix of this Markov chain are 1, 0.57 and minus 0.07. Let's look at another example, the example of a random walk on 4 states with perfect reflection. If you look at its eigenvalues, the eigenvalues associated with one-step transition probability matrix of this Markov chain, which is a 4x4 matrix that you have already seen, the eigenvalues are 1, plus 0.5, minus 0.5 and minus 1. I hope you have seen a difference here compared to the previous two cases where there was only one eigenvalue with magnitude 1, but in this case there are two eigenvalues with magnitude of 1. One is plus 1, other is minus 1. Let's look at another example, the famous example of a person trying to perform Hajj. If you take its 8x8 one-step transition probability matrix, then you will get 8 eigenvalues, and 3 of those eigenvalues are going to have magnitude 1. If you actually perform the eigenanalysis for this case and find the numbers which are the eigenvalues of this 8x8 one-step transition probability matrix, you will see that the 3 eigenvalues with magnitude 1 are 1, and then 2 values are complex values. One eigenvalue is 1 and 2 eigenvalues are complex numbers, and they are minus 0.5 plus minus j 0.866. If you look carefully, if you plot these numbers on complex plane, you will see that they are on a unit circle. Of course they are on a unit circle because I said that they give a magnitude of 1. So one is on the right side on the x-axis and other is on 120 degrees where it is minus half plus square root of 3 by 2, and other is minus half minus square root of 3 by 2. So they are located at 120 degrees apart positions, and one is at horizontal x-axis. If you look at the previous case where we were talking about a random walk on 4 states, the two eigenvalues with magnitude 1 were 1 and minus 1. So they were on the unit circle and they were 180 degrees apart. Actually, these eigenvalues represent complex roots of unity. There are two complex roots of unity which are 1 and minus 1. I'm talking about second root. And there are 3 third roots of unity. One is 1 and other is that minus 0.5 plus square root of 3 by 2 j, and minus 0.5 minus square root of 3 by 2 j. So if you have a periodic behavior of a recurrent Markov chain that does not have a unique eigenvalue with value 1, then you have multiple eigenvalues with magnitude 1, and they are roots of nth roots of unity, second root, that is square root of unity, or the third root, the cube root of unity, which are 1 and the two complex numbers. So this should give you some idea why some recurrent Markov chains have a unique convergent n-step transition probability matrix and some do not. It all lies in the values of eigenvalues. If a one-step transition probability matrix has a unique eigenvalue, simple eigenvalue of 1, then it will converge. There are other conditions that we are going to discuss now. The other conditions that other eigenvalues and eigenvectors must fulfill so that n-step transition probability matrix converges can be analyzed through the idea of diagonalization. We have already talked about diagonalization, and we are going to apply that idea to diagonalize the one-step transition probability matrix P. You can see on your screen that if P is diagonalizable, then P can be written as multiplication of three matrices, V inverse times D times V, where V and V inverses are formed from the eigenvectors and D, which is a diagonal matrix, is formed from eigenvalues. So D has only diagonal elements which are non-zero, which are the eigenvalues, and all other entries are 0. This V inverse and V have columns which are eigenvectors. So if we want to find the higher powers of this matrix P, you can take the higher powers of this representation of P where we have three matrices, and if you take higher powers of this V inverse dV, then all neighboring V inverse and V, they cancel each other out, and you get a representation which is V inverse times D raised to power n times V. Let's have a look at this matrix D raised to power n. This matrix is higher powers of a diagonal matrix which we get out of the eigenvalues of this matrix P. So if lambda 1, lambda 2, all the way up to lambda capital N represent the n eigenvalues of this matrix P, then D raised to power n is just higher powers of these eigenvalues. So if lambda 1 is the first eigenvalue of P, then first eigenvalue of D raised to power n will be lambda 1 raised to power n, and so on. Now suppose one of these eigenvalues is 1. Let's assume lambda 1 is 1. Then in higher powers of D, this number lambda 1 raised to power 1 will remain 1. And if we assume these other values, lambda 2, and if you assume these other eigenvalues, lambda 2, lambda 3, all the way to lambda n, have values which are not equal to 1, then higher powers of Dn will contain values which depend on the actual values of these lambda 2 to lambda n. If the magnitude of lambda 2, lambda 3, all the way to lambda n is less than 1, then higher powers of Dn will have these terms approaching 0. They will become smaller and smaller and smaller, and eventually in the long run you will have a D raised to power n which will have just 1 here, and all the entries will be 0. Now can you imagine if you take a higher power, very high power of Dn, and it gives you a diagonal matrix with just 1 in one place and everywhere 0? Put that D raised to power n here, and you will see that this is going to give us a constant value, and that constant value is P infinity. If you take higher power of P, Pn, and take n higher and higher, and it gives you a d raised to power n for very high value of n with 1, 1 and others 0, then this expression is going to give you the final p infinity. One word of caution again, that in this diagonalization procedure, if you are relying on MATLAB to find eigenvalues and eigenvectors, then you have to be careful, because MATLAB always gives you a diagonalization based on the concept of right-sided column types eigenvectors, where in this case we are working with left-sided row types eigenvectors. Now let's have a look at a few examples of simple Markov chains, their one-step transition probability matrices and its diagonalization, and then higher and higher powers of D, which is the diagonal vector, diagonal matrix obtained from all the eigenvalues. The first example that you see on your screen is that simple machine which breaks down, and it has a D of a diagonal matrix of 1 and minus 0.1. Remember, these are the two eigenvalues. If you take higher and higher powers of this D, of course D square will have 1 and plus 0.01, and D raised to power 4 will have 1 and 0.0001. If you continue to take higher and higher powers, you will end up with 1 and everywhere else 0. The next example is modified Markov chain of this machine, and here the three eigenvalues are 1, 0.57 and minus 0.07. One eigenvalue is 1 and others have magnitudes less than 1. So if you take higher and higher powers of this diagonal matrix, you will end up with a matrix which has 1 in one location, and all entries are going to become smaller and smaller and eventually going to become 0. The next example is that of simple random walk, and the diagonal matrix is shown here, where eigenvalues have been rearranged in such a way that 1 and minus 1 are shown on the top and plus 0.5 and minus 0. On the bottom. So if you take higher and higher powers of this diagonal matrix, you will not get a single one, but the higher and higher powers are going to again switch between two matrices. If you take a power which is even, you will get 1, 1 and then all zeros, and if you take an odd power, you will get 1 and minus 1 and all zeros. So all these ideas should give you a clue how a sequence of converging matrices give us a recurrent chain with a stable distribution, and a sequence of switching destination matrices give us a non-unique stationary distribution set. And the reason is that if there are more than one eigenvalues with magnitude 1, then these eigenvalues in that diagonal matrix are not going to vanish with higher and higher powers of this diagonal matrix. I'm not going to show you the actual matrix for that example of 8 by 8 one-step transition probability matrix representing the situation of a person trying to perform Hajj. Only thing that you should notice is that there are 3 eigenvalues with magnitude equal to 1. So if you make a diagonal matrix with those complex valued eigenvalues and continue to take higher and higher powers, then those 3 locations will not give you 0 valued results. Those 3 locations will switch between different values and they will stay there. Hence, you will have a periodic behavior where there will be 3 matrices which we'll get depending upon if the power is divisible by 3, if the power gives a remainder of 1, or if the power gives a remainder of 2. So in today's lecture, we analyzed the behavior of one-step transition probability matrix through eigenvalue and eigenvector concepts. We saw that if a recurrent Markov chain has to have a stable, unique, stationary distribution, then the sequence of matrices obtained by taking higher and higher powers of one-step transition probability matrix must converge to a unique matrix. And for that to happen, there must be one eigenvalue with value 1, and other eigenvalues must have magnitudes less than 1. Then if you take higher and higher powers of this one-step transition probability matrix, the diagonal representation shows that you are going to eventually get a stable unique matrix. If there are more than one eigenvalues with magnitude equal to 1, then we have a periodic behavior, as we saw in examples 2 and 3. In coming lectures, we'll continue with our analysis of Markov chains and its classification and its long-term behavior as recurrent or transient or periodic and other types. Till then, I wish you the best. Thank you. Khuda Hafiz.